Hello everybody, Mr. Hennon here, and as you can see, I'm in the classroom. I even have, if you kind of look over here, you can kind of see some plans for Physics 1, some plans for Physics 2 over there, and we're kind of ready to start. So these notes are going to be over Chapter 19, and I want you to kind of work on them after you've kind of finished up all the stuff from Chapter 18. We're going to end up having a Chapter 18-19 test because that's going to be all kind of clumped together. But this one's going to introduce two major things. It's going to introduce the idea of potential energy and potential. They are actually different. And one of the first things I think is good to kind of start off with is this idea. Let's relate this to gravitational potential energy. If I have a basketball sitting up here in the air, and I am looking at it, we know that this basketball has a certain amount of gravitational potential energy at a certain point. And then if I let the basketball fall, its gravitational potential energy is going to decrease. So it's going to go to a lower value here. And basically what's going to happen is work is going to be done by the gravitational field to move it from high potential to low potential, high potential energy to low potential energy. Well, the same thing would happen if I had some kind of charge. Let's assume this is a positive charge, because we usually always do our test charges as positive, Q0, and I put it at this point right here, and then I let it go. What would it do? It would tend to want to move toward this negative plate down here, and so we would say that its electric potential energy is going to decrease, and basically work is going to be done by the electric field to do that. And so we could calculate that change in electric potential energy. Here's the cool part. If you write it like this, the charge times the electric field times the distance it is away from the source of the electric field, that is a way of finding the electric potential energy, just like mass times gravity, which is actually like a gravitational field. It's newtons per kilogram times a height or a distance away from whatever is creating it. Now, in this particular case, it would be a little bit difficult because you actually have two things that are producing this, but they're going to produce an electric field that would point in this direction. It would go from the positive, and so you would talk about, you would probably measure from the bottom up to those particular points. The other one is electric potential. So electric potential is really just defined as the electric potential energy divided by the charge. So it's kind of like electric field is to electric force. Electric potential is to potential energy. It takes away that test charge. And so when we talk about electric potential, we talk about it being in joules per coulomb. This should actually be a capital J, sorry. And a joule per coulomb is the same thing as a volt. So when we talk about voltage, we're actually talking about how many joules per coulomb this test charge has. So again, as you move between these two different points, you're going to have a difference in electric potential. Now, here's one of the key ideas. Notice that they write the difference between B and A. So as you start at A and then move down to B, what is the potential difference between those points? It's the difference between the energies, but B was at a lower energy than A was. And so because of that, you can actually get a difference in voltage or a difference in potential. V is actually going to be used for potential. And in this case, it would be the opposite of your work per unit charge. So in other words, the change in electric potential energy, we have the field do work to move it that way, but we're actually going to be talking about the more energy you have, the more potential you have. So here, let's try a little sample problem. Let's say that you have a positive 2 microcoulombs here, and it's at position A, and you're gonna let it move. Sorry, the thing doesn't always register my pin when I do it. And it's gonna move from point A to point B here. And that is going to have the electric force, the electric field is going to do 5 times 10 to the minus 5 joules of energy moving that. So the difference in potential energy between these points is pretty easy, and then the electric potential difference is going to be the same idea. So the change in potential energy is just going to be the difference between those energy points But we often talk about it being negative. So it's decreasing as it goes from A to B, it's actually decreasing that energy. So that 5 times 10 to the minus 5 joules is going to decrease because this is at lower energy than this is. That also will allow us to figure out what is the potential difference between these. So we talk about the difference in potential, and it would be negative 25 volts. This is basically because we tend to think of, when you think of the voltage across something, so if I connected this to some kind of voltage, we would say this is at, say, a positive, let's say 200 volts, and we often say negative is at 0 volts. And so when we're talking about this, if I go from positive toward the negative, I am decreasing my voltage. So I'm going from 200 down to 0. If I went from 0, I could increase the voltage up to the positive. So again, we're always thinking of the way positive charges are moving, which is kind of weird. And that's what this is talking about. If I were to put a positive charge right here at point C, it would move from this lower potential toward the higher potential. So it would move from C to A if it was a positive charge. And we often talk about positive charges. If it was a negative charge, it would actually be moving the opposite way. It goes from a higher potential to lower potential. That's why we typically use positive test charges, because they make more sense. They follow our kind of general idea. Water, fluids flow from high pressure to low pressure. Heat flows from high temperature to low temperature. Charge, positive charge, should flow from high potential to low potential. But in this particular case, we talk about kind of the difference. And so this one's kind of a weird one, that we want to actually have our charges moving in a particular direction. So this is kind of, if we talk about this positive charge, this is where the positive charges would want to end up. And if we switch this out for a negative, if this was a negative charge, it would tend to go up. So we end up with negative charges up here, and so we get them moving. So negative charges are going to move from lower potential toward higher, whereas positive charges move from higher to lower. So that's why we're going to probably stick with that general idea. It's kind of a weird concept. Potential, I don't really like it, electric potential, but we use the concept of voltage. Here's another example. Let's say I have a particle that has a certain mass. So this 1.8 times 10 to the minus 5 kilograms, and a charge of 3 times 10 to the minus 5 coulombs. It's released from point A and accelerates horizontally until it reaches point B. So this charge starts at point A and it's going to move there. And it says the only force acting on it is an electric force, and the electric potential at A is 25 volts, or 25 volts greater than at C. I don't know what that means. This should be 25 volts more than at B. So sorry about that. That's a typo on my part. And it says, what is the speed of the particle at point A, or point B? Sorry, can't speak. So for this one's kind of an interesting one. What we're basically going to end up doing is we're going to use energy conservation. So we've got, at these two different points, we've got kinetic energy and potential energy, but now it's electric potential energy. If I rearrange it, if I want to figure out how fast it's moving at point B, then I'm going to take into account all of these parts to it. The kinetic energy it has, that 1/2 mv squared, it's potential energy. And then the easiest way to do the potential energy here is to go back to the basic definition of potential energy, the fact that if I was to take this, electric potential energy could be written as a charge times your voltage at a particular point. So that just makes it a little bit easier. And since we're talking about a difference here, that's where that comes in. But this difference in voltage is the 25 volts that they mentioned up here. So from between the potential between A and B, A is 25 volts higher than B. So it's changing by that much. We've got the charge in there, we've got the mass. And really what we're doing is we're setting kinetic energy equal to electrostatic potential energy. We're going to use this a little bit because one of the things we're going to talk about is the Rutherford experiment. You're going to have this idea, and that's basically what Ernest Rutherford came up with, is as these charges were coming in, they were being affected by the atom, and this was affected, and kinetic energy equaling potential energy was a key idea. Another concept, if I start talking about the work done by elastic or electrostatic potential energy, and I talk about the work and I switch it out for what the equations are. In other words, I use the fact that the electric field is equal to KQ over R squared, I can actually get this little combination to give me this. And this K, Q, Q0 over R is a way of finding the electric potential energy between 2 point charges. We can also say the electric potential of a point charge. Hey, do those two equations look familiar? They should, because we know that Coulomb's law says that force is K Q1 Q2 over R squared, and the electrostatic field, or the electric field, is K Q over R squared. So they look the same. Electric field is related to potential, except that we've gotten rid of the squared, it's just R, and force is related to energy. Really, where this kind of comes from is the idea of finding the work. Work is force times the displacement, so that's why that displacement comes out. So if I had some charge, this particular charge here, and another little test charge there, it's going to feel a force because it's positive, and it's going to move from higher potential when it's closer to this to lower potential. So we could actually calculate the potentials, or we could look at the energies. Use this idea. Let's say that I have a point charge right here, this 4 times 10 to the minus 8 coulombs. It's going to alter the electric potential at a point 1.2 meters away. If I were to put a positive test charge here, it would feel a positive 300 volts because I could calculate everything due to this particular charge. It doesn't matter what that test charge is, but I could actually find it. If this test charge happened to be a negative test charge, however, the only thing different is it would be now at a negative 3 volts. In other words, as you get closer to this, you're actually going to be at lower potential, and you're going to get closer to 0 the farther away you get. This equation, actually I'm going to go back for a second. In these two equations, we don't actually keep the sign. We just put in the quantity. For these equations, though, we do actually want the sign. So actually change that a little bit. We want the sign when we're finding the potential. We actually want the sign when we're finding the electric field, because electric field can be, well, actually, no, we wouldn't want the sign there. Drop what I just said. I'm sticking with this. These energy and voltage, those are the ones that we want the sign. Force and electric field do not want the signs on your charges. Sorry about that. Here's another one. If you wanted to find the total electric potential at a particular point, electric potential is a vector. So it has a kind of a direction. It's not actually a vector, but it does. Okay, start this over. It's not a vector, but because it has a sign, when you're combining them together, that sign is going to be important. So for example, if this is a positive 8 and this is a negative 8, if you are smack dab in the middle between them, this negative 8 is trying to decrease the potential there, and the positive 8 is trying to increase the potential there. Those would actually cancel each other. So if you notice, the potential in part B here is 0. But when you're over at this particular point, this one is closer, so it's going to increase the potential. You're going to be at a higher potential. This one is decreasing the potential, but doesn't decrease it as much as this one is increasing because it's farther away and it's an inverse relationship with distance. And so you would end up with a positive voltage or a positive potential at that point. Little side notes, concept question here. And that's basically what this notes is. Once we get the equations, it's kind of some concepts we're looking at. There are 2 points that are along the line between these two charges where the total potential could be 0. And here what we have to think about is a point right here. Whoops, a point right here would have a potential equal to 0 because this one is trying to increase the potential and this one's trying to decrease the potential. And so it's possible if you get close enough to this one that this increase and this decrease would be the same and they would cancel. So this is going to be one point where the potential could be 0. The other one that's kind of neat is if you get out here, this one is trying to decrease the potential. This one is trying to increase the potential. And so if you get far enough away, it is possible that these two could also be the same. In other words, this would be a little more deeper as we're doing it. So we could be on the outside. Could you be over here on this side? And the question, the statement is no, because the farther away you get from this particular charge, the less potential you're going to actually get. I actually have been drawing these slightly incorrectly. I should actually be drawing them. Let's see if can I get rid of everything? Let's use the eraser. I should actually be drawing them as the largest potential when I'm at the object. Here we're going to do in green. Let's switch this out. So this would be a really high one, and it's going to start to kind of drop down up here. And this one would be a really low one, and drop down to there. Because the farther away I get from this one, this is going to be the lowest potential. And then as I get farther away, it's going to get closer and closer and closer to being 0. And this one, as I get, this would go up, but then it would suddenly switch and we'd get that one. It would start to get 0. So it's possible if you got way, way, way over here to the left of this one, you might, but since it's always going to be closer to that one, it's highly unlikely. And then this one is going to be negative. It's going to kind of be curved like that. This one's going to start out positive. Maybe as we get over here, the positive and this negative would be canceled, and those would be canceled. So just a little side note. The last little bit is on what we call equipotential surfaces. We know that if I have a little charge here, it's going to produce an electric field that's going to be a series of lines pointed away from it. So this red is the electric field, and it would just be moving out. And the thing we do is we draw little equipotential surfaces, spheres in this case, around a point charge, where the electric field is always perpendicular to the surface. And what that means is that if you move along this surface, you would be doing no work. So if I were to go from point B up to point C and I stayed on this equipotential, you wouldn't have any work to move between them. So, and this comes back to, if you remember, we talked about that all the charge wants to spread on the outside of it. When you're talking about charges, they tend to spread out on this. And so to move along that surface where there's the same quantity of charge, you don't have any work being done. And a better picture here is we've talked about this little positive and negative charges and creating an electric field. Those red lines are the electric field. Let's see if I can make sure we label that one. So the red lines are our electric field. And then these blue lines are what we call this would be the equipotential or the voltage lines. And notice that everywhere this line is, they're always perpendicular. Not really something you need to worry as much about, because we won't really get into it until we get in, if you get into higher level electromagnetism in physics. The last little one is an example of having a couple of charged plates. We're going to do something with the Millikan experiment. And so this one's kind of a neat one. As I go from this positive plate towards this negative plate, we can talk about these little equal potential surfaces. And because we have an electric field that's moving between them, and if I knew the difference, in my charge here, or my potential here, between these two plates, or between this plate and that plate, I can find out some other ones. So the difference between this one and this one, they mentioned, is -3. The difference in electric potential here is negative 64. Now, the reason why they're using negative is they're assuming that you're starting out here at 0 and they're making this be negative 64. We could also do a positive 64, but we're going from B towards A if you're a positive charge, or if you're a negative charge, so that's where that's kind of coming from. So another way of finding our difference in voltage is to actually take the electric field and multiply by the distance that it travels over. And this is why another way of, we know the electric field is force over charge, but another way of thinking of the electric field is it can actually be a difference in voltage over a difference in distance. Now they're using S to represent that distance. I often just kind of label this with a D. So I already write a D here. So when they say what's the spacing between, I think they're using S for spacing. That's where they're kind of coming from. So that's why the electric field has two interesting units. It's a Newton per Coulomb, or it could be a volt per meter. Those that have me in physics 1, we watched a lightning video where it talks about lightning and things like that when we were getting into electricity, and they kept measuring the electric field by saying we're waiting for it to be 15 kV per meter. So they wanted 15,000 volts per meter. It was a way of measuring the electric field in the air. When that happened, they thought there was going to be a lightning strike. So since the electric field is going to stay constant between these plates, what they're doing here is they calculated the electric field as so many volts per meter, and then we just substitute that in there with the difference in voltage between those 2 points, and we've got it. It doesn't really matter whether you use a positive or negative charge here. I have really just kind of put everything as positive before, so I'm not sure why the book decided to put in the negative. That's a whole bunch on chapter 19. I hope you got something out of it and answer the little Google form questions, and we'll work on some problems next week. Take care.